Moving on now with the last stage of my schematic review, which is the label review, where I review every single label that I have in my schematic. So I've generated a list here with all the labels, and I've started reviewing some of the labels in the last video. I'm going to continue reviewing these labels, and I have quite a few here, but luckily it goes very quickly to review the labels. So let's get started. CanFD master in, slave out. This one goes to CanFD transceiver or CanFD interface. Master in, slave out is connected to SDO, data out, and then it's connected to SPI 6, master in, slave out. Awesome. So that one is green. Let's see, that one is green, and the next one is kind of the master out, slave in. This is really annoying. I can't copy properly from the calc application, but let's see what this finds here. So master out, slave in, SPI 6, that's correct, and over there, yep, that one is done. The clock, connected to clock there, and here it's connected to SPI 6 clock. Great. So doing this after reviewing all of the components is, I think, the correct sequence of structuring the schematic review, because now that I know that components are correct, I can also make sure that any labels are connected to the correct pins by just looking at the component at the pin names on the components. So we make this one green and start a frame signal. And this is going to copy in this weird character, which I have to remove. Start of frame is connected there, and start of frame is connected to just the GPIO pin. However, what I could do here actually is let's see. So I was thinking that maybe I should connect the CanFD chip select to the pin that can be mapped to SPI 6 chip select, but I think that for the most part I'm never using the built-in chip selects, so I'm using just normal GPIO pins for both the CanFD and the EtherCAT chip selects. So this doesn't really matter, so I'm going to keep it the way it is right now. So we can make sure that, let's see, this one, this is the component review. I'm gonna save this and close this, and then I'm going to bring up the label review. So this one is green. Can Rex 1. Rex TX, and then this has to be connected to can Rx. Yes. So we can take CAN RX1 and CAN TX1, and then CAN RX2, and CAN TX2. CAN 2RX, CAN 2TX. Awesome. CAN standby 1. Standby 1 and standby 2. And this can be connected to just any GPI pin. Standby 1, standby 2. Alright. So these standby pins, I think if I need to connect any, if I need to free up any GPIOs, then I may just connect these standby pins to make sure that the transceiver is always enabled. But for now, I'll just green light them. DC calibration mode. Connected there, and then to GPI pin, to test point. Okay. So DC Cal 1 and DC Cal 2, are they even connected anywhere? Nope. Now what about gain? Yeah, gain is connected, but DC Cal is not connected, which means that we need to copy DC Cal. We need to connect it to some pins. I still have a few pins here. Let's see if I think I'll just use the standby pins here, because DC Cal is more important. DC Cal allows to put this gate driver into DC offset calibration mode, where you can read out the current sense outputs, and you'll get the DC offset of the 0 point of the current sensing circuit. So this is more important. Let's put this CAN transceiver actually into being always on. Let me just open the data sheet. Low level on standby selects normal mode. Yes. So low level on the standby pin. I can just delete this one. Delete this label and this label, and then I'll just connect the wire here to the ground. Okay. this one and this one, and I'll connect the DC cal and DC cal 1. Okay, I can greenlight them, and I'm a little bit worried that there are certain, there are a lot of pins here that I can see for sure are not connected anywhere. So question is if we have enough pins on the microcontroller left in order to be able to connect all of them. But we'll see. Let's move on. KiCad CS. Connected to a GPIO pin. Can greenlight that one. KiCad RQ. Is connected to the EtherCAT and a GPIO pin. That's good. KiCad MISO. Connected to SO, MISO, and MISO there. SPI 6. KiCad MOSI. Connected to SE and MOSI there. So that's fine. KiCad reset. Reset there and reset there. Cool. So it's quite possible maybe I will just connect the EtherCAT reset to the one pin I have left on the SPI GPIO expander, and maybe free this pin up for something else. So that's a second. That's another pin that I can use perhaps for something else. But for now, I'll just greenlight that one. And KiCad SCK. It's connected to SCK there and connected to SCK there on SPI 6. So that's fine. KiCad Sync 0 is not connected. Now, sync latch. This is for this I have to actually open the datasheet. Let's see, where is the datasheet? There. Now this is a schematic, this is not a datasheet. Let's see. LAN 9252 datasheet. Pretty sure I have it somewhere. Maybe this is the datasheet. Yes, this is the datasheet. Okay. So it doesn't matter now which one I use. I'll just use one of the docs. Let's see. So sync. Gonna search this for sync or latch. We can actually search for sync 0. And it would be nice if I could get some description of what this pin actually does. Okay, EtherCAT core provides 2 input pins, which are used for time sampling of external events. So what exactly is the typical use case for these pins? Let's see. It seems to me, having a quick look on this datasheet, it seems to me that sync and latch are related to the parallel interface. So that whenever you need to sort of latch the inputs, you provide a rising or falling edge on the latch signal, and whenever something else, whenever like a network connected device writes to this LAN 9252 and causes it to update the outputs, then it outputs a pulse on the sync signal. But I'm not sure if there is any other use case for this. External events. Alright, so you can configure the chip to synchronize the outputs using one of these signals. But is there anything else? Sync latch. Okay, so there it's used for the output data sample selection. Input data sample selection. Sum 0, sync 1. Okay. And you can configure the pin to be either sync or latch. Okay, so, and it's also possible to read that, I think, from the over SPI. Right, the other register that that contains the states of these pins. Okay, so it seems to me that this is not that important. Or at least not important enough to warrant a dedicated connection. So I think what I'll do is I'll remove these two, and I'll just add 2 test points. So that I at least have an option to solder something there. But I don't think that I'll be using this because I'm not even using the parallel interface. Alright. EEPROM SCL. connected to SCL there, and connected to SCL on I2C1. Yes. Cool. We can do the SDA at the same time. And that's connected to SDA there. So SCL and SDA are correct. Write enable. Connected to GPIO. This is also one of these pins that can be used for something else if necessary. So, so I'll green light that one for now. And then we have INC 1 VDD 5 volt. Comes out of this power management IC, 900 milliamps, and connects to all of the connectors on encoder 1 and the capacitors. And we have a bypass, optional, and we have yeah, and we have this PWM input, or we have two of them, where one is driven by the first encoder supply, and the other one is driven by the second one, supply management chip. Okay, and let's look at number 2. Connected to output B, connected there, and the bypass and the PWM connector. Okay, that seems to be correct. And then we have encoder A1. Encoder A1. This has to be connected to timer 2, channel 1. And encoder A2. Actually, let's see which one is the next one. Yeah, let's look at the encoder A2, and that has to be connected to timer 4. So we have timer. Let's see, timer 2 is encoder for the first motor. Timer 4 is encoder for the second motor. So channel 1 there as well. And then we have encoder B1, which follows the same pattern, but here we have channel 2 on timer 2, and encoder B2 is connected to timer 4, channel 2. Encoder C1, or Z actually, yeah. Encoder Z1 is connected to, let's see, this would be a GPIO actually. So this is not related to timer 4 in any way. And encoder Z2. Yeah. So these two will be just GPIOs. Alright. So we have encoder 1, encoder 2, B and Z. The Z pulse is delivered every time the encoder makes a revolution. So your counter counts up to the certain number of ticks, and then every time your encoder makes a revolution, the Z pulse is generated. And that makes it possible to synchronize to the exact number of revolutions. just in case you miss some encoder counts, for example. Encoder CS. So this is an SPI chip, so we have a CS. We can search for encoder CS1, connected to CS there, and it's connected to a GPIO here. Encoder CS2, connected to CS there, and the GPIO here. Encoder RQ1. This signal will be delivered if there is any fault on the encoder wiring. So it has to go to a GPIO, and it's connected also to the motor brake input. So this has to go to timer 1. Let's see, timer 1 brake input. Has to be here, yeah, brake in. And number 2 is connected to brake 2. Timer 1 and timer 8. Timer 8 brake. Great. So we can green light both of them. And we have encoder MESO 1 and MESO 2. MESO SDO and MESO there connects to SPI3 MESO. And number 2 is connected to SDO there and SPI MESO. And MOSI goes to SDE and MOSI there, SPI3. And SCK1 goes to SCK there and SCK there on SPI3. And number 2 goes to SCK there and SCK there. Yes. Great. So this is all connected. MOSI and SCK. And encoder OC1. This is from this power management IC. This is going to be triggered whenever there is either a short circuit or something is connected that draws too much current, so that this chip is forced then to turn off the power supply here. So it's good to be able to read those signals. We have both of them connected to the SPI expander. So when this signal is triggered, this interrupt will trigger GPIO int A, and then the microcontroller will have to read out the signals from this chip to determine if this bit is reset. I think it's going to be actually active high, so it's going to be set if there is an overcurrent condition. Number 2 is connected also to there. Great. So overcurrent is okay. Power enable. This is going to be connected to GPIOs, and power enable 2 is connected also to the GPIO. Great. Enc SG, signal G1. This is one of the extra inputs. This one goes to just the GPIO. I wonder if we ever need to Which actually brings me to this idea here that maybe 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 it makes no sense to have this chip here. Let's see, where is it? Where I have the PWM inputs. Maybe this is just like, I kind of felt from the start that having this chip here is kind of like, I'm just using like 2 inputs on it, and everything else is just waste. So what if I were to use the PWM inputs from one of the extra inputs on this chip? I think this would be much better. I'm gonna just see what break is connected to. Is there a break connection here somewhere? Let's see. Motor 2. No? Did I totally miss adding this anywhere? It certainly seems this way. Yeah. Okay. Whole lot of problems here. This is not good. Okay. So the break input, I'm gonna use one of the extra inputs here to act like a break input. Now, before I do that, I want to double check that Max 14890 supports configuration of those outputs as open drain. Because I have an interrupt pin there connected as an open drain, so it would be good if I can configure this pin as well to be open drain, because otherwise it will not work. It will just short to positive supply. So it has to be open drain. But it could be that this chip supports open drain on some outputs, but not all of them. So I have to double check this. And also I want to see if the inputs support like 3 volts or 3.3 volts. Okay, this should be fine. It's like up to 20 volts. And can we configure it as open drain? Okay, is there any description of all the pins? Maybe it says in the table somewhere. Receiver output, that's the only thing it says. seems to me so far that they are driven pins, like push-pull pins, but maybe there is some configuration option for that. I'm gonna search for the RQ just to see how they word any open drain, like what they say about an open drain pin, because RQ is probably an open drain pin. And I want to see if there is any notion of that. Note 5. Okay. So fault signals are open drain, but it seems doesn't say anything about any of the other outputs. Okay. What about push-pull? I'm supposed to have 2 matches, but only one comes up. Push, pull. Okay. So let's have a think about this. So this one will be open drain, and then this one, if I use the number 3 for break, this will be a driven pin. And then there will be a pull-up of 50K inside the STM32. Let's see the current for these pins. How much current can they support? Okay, so we have to be careful there not to connect them together so that they don't short. And I'm just thinking, what would be the best way to combine them? so that they properly work together with minimal number of components. So I don't want to like have to put any buffers or anything sort of that's more expensive than just some passive component at most, like a resistor. But I wanna see if I can come up with some good way to do this. Let's see. Let's have a look. Let's see if we can get some ideas here. Connect an open drain. This seems like yeah, so if I use some Schottky diode with very low voltage drop, then this actually does make sense. But I still have to be careful there, because I could end up with unintended side effects. Okay, so let's just have a look here so that we don't. Yeah. So if I use SY, I currently have SY connected. What's up with that one? That has 4 connections. SH2. Connected there. It's connected there. It's connected there. Yeah. All of this needs to be fixed. So let's see. Let's make, so the question is, next question is, do we need 2 break inputs or only, yes, we do need 2 break inputs actually. So I'm gonna use this one as the break. Actually, this would be motor 2. And I'll need to have a diode here though. Let's see. Let's use a BAT54. Okay. So when this one pulls, it will pull the current through the diode and to the ground. And when this one is driven, nothing will happen here. or it will be just a small voltage. But I'm gonna simulate this just to make sure that this is gonna work as intended. But let's see first here. So we have the SPI. I'm gonna rotate this one to make some room here, like this. And I have this RQ. And I think I'll remove that label actually, and I'll do it like this. So this will go through the diode here. Like that, and this will go to the motor 2 brake input. So then we should be able to pull this one low so that this one goes low as well. And the RQ will go low if anything goes wrong here. So this should work as intended. But then, let's see. But then I have to remove that label there as well. Let's see. Ink SY. So ink SY1 and SY2. So these two will be deleted. And then we have and then I'll delete this one, and I'll just connect this as a motor brake input. So remove that resistor as well. I'll move this one here. And then we have the same thing for motor 1, but it's down here. Come on. Down here. Let's remove the junction, the wires. I have to make sure that I don't forget any little detail here. So I'm removing the labels for the RQ, and I connect the motor 1 brake there, and then I have to go back here and let's see, and I'll just do this. So the Y label goes away and is replaced with this diode. And then we have the brake here. Yeah. See, that's not really necessary because we can just do like this. So because I'm removing this label completely, I can just do like this. And I have enough space for all the labels here. Alright. So then when our queue pulls this line low, then this line goes low. And when this one pulls the line low, then this line goes low as well. Looks good. But just in order to be sure, I'm going to test this in LTSpice. And I'm going to test it with the values of the pull-up resistors in the STM32, which is 50K. Let's say we have a pull-up resistor there, we have a voltage source. This would be our interrupt, and let's say this would be our actually, let's do it like this. Let's use a switch. And then I'm going to move this. Let's see. Control R. Have to have this voltage source upside down. No. God damn it. Undo. Everything is backwards in LTSpice. Everything. Even zooming is backwards. Like, rolling the wheel backwards zooms in. Rolling the wheel forward zooms out. Incredible. All right. So this will simulate the open drain, and then we have this one will be the push-pull connected through the diode. Yes. Let's see. Rotate this one. And put it there, and then we connect this to ground. Yeah. Okay. This would be a BAT 54. Yep. And then this will go to, so the pull-up will go to 3.3 volts. It should be another voltage source here. Let's see. Okay, and this one will be a pulse, so I'm going to go to pulse. Let's make this initial 0 and 5, delay t on 0.1, t period 0.2, number of cycles unspecified, and then this one will be a similar thing, but I'm going to make this, let's see, so 3.3, delay 0.05, no, damn it, so 0, 3.3, delay 0.05, rise, fall, t on 0.1, 0.2. So hopefully we get something that makes sense here. And this one is going to be just a constant voltage of 3.3 volts. Let's see. Oh, so let's switch. I think I need to import a library, but I don't remember which library, so I have to look it up. Let's see here. LT spice switch. Okay, right, so it's we need to specify this as let's make this switch, and then let's make an op here. So this would be model switch SVR on R off. Yeah, one meg, of course. VT 0.5, VH 0.4. So I think this is like the voltage thresholds. But I'm just going to try it with this settings, and then let's see if we get any result here. So. Right, so this is what it looks like, and we can also draw this this line. This is the, let's see, this is our open drain output, and this is our push-pull output. So push-pull output goes high, the voltage, let's see, the voltage here, let's see, right, so the open drain output goes high to 5 volts. This switch is closed, so this has to be right. So the switch is closed when this one is high. This would be like the open drain output going low. So then our voltage is at 0.7 volts, which could be too much, because, let's see, oh, the diode has to be rotated, so the diode has to be the other way, like that. Let's see, this is much better. So we have our open drain output going low, our push-pull output going high. This one is still low. Open drain output goes high. This one goes to around 3 volts. then both, let's see, then push-pull output goes low, and then the voltage drops to around 1 diode voltage drop. Yeah, and then yeah, so this is this should work as intended, and it should have very it should have around 0.2 volts when it's low. So this should be precisely what I need for this. Let's see, for this solution here. Okay. Let's see. So, motor 1 break in. Okay. Let me see here. Alice, backa, nej, backa, sit, backa, så, bra. My dog needs to go out and have a shit, so she's gonna try to use every means possible to tell me that she has to go out and have a shit. So I have to, unfortunately, pause this video right now and assist her with going out and having a shit. Alice, sit, bra. Los, bra, sit, så. Vänta. So I'm going to pause this video.